I have just one idea that I would like to propose, and then feel free to come up to me afterwards and give me your opinion. And I'm going to start with a page of Eiffel code. This is the Eiffel programming language. To illustrate something that Bertrand Meyer, the guy who invented Eiffel, calls design by contract. This was a programming language that came out about the same time C++ came out and competed with C++ for mindshare and lost, pretty much, to C++. But he had the idea of that you would not just implement a function, but also specify and test the behavior of the function all kind of together in the same source code. So the do part of the function there, the middle part, is the actual algorithm of square root. Then there's these two other things, require and ensure. And require he called a precondition, and he said that that is a part of the contract of this function that is the responsibility of the caller. So it's not your fault as the implementer of the function if x is less than or equal, well, less than 0. And it's the fault of the caller, and that's their bug, and this function is going to throw an exception. So that is an assertion, essentially, that was expressed in the code as part of the contract, the specification of this function. And at the bottom, there's an ensure clause, which is a postcondition, he called it. And a postcondition is also an assertion that says what you, as the implementer of this function, are supposed to do. So that's what your responsibility is. So that's called design by contract. And the idea was that assertions would run when the program runs. So like little tests that run as the program runs. By default, require clauses are enabled and ensure clauses are off in Eiffel. And that's kind of what we did in the Java community. So this didn't take off. This language really didn't take off that much. And C++ sort of won out. And it did not have this, did not have design by contract. And Java came along, and it also did not have design by contract. So in Java, what we do is we express the contract of a function mostly in English. So we do check preconditions, and we don't turn them off. In Scala, there's a nice predef called require, method in predef called require, where we can kind of very nicely say this square root function requires certain preconditions. That's the responsibility of the caller. If the caller doesn't fulfill their obligation, we reward that caller with an exception, right? Illegal argument exception. And then the rest of the contract is stated in English, saying this is what the thing's supposed to do. Anybody who re-implements this method with another algorithm in a subtype someday would need to fulfill that contract. So that's the same concept, but it's not in code anymore. It's in English or some human language. And then what we did is we moved the post conditions over to this other completely different area called the tests. And what did actually take off in at least the Java marketplace of ideas was test-driven development. This was well marketed by Kent Beck and Eric Gama, the two guys that created JUnit. So this really took off in the Java community. And so what we do is we do tests off to the side. And this one is called example-based tests because I just pick certain examples and try my function to make sure it fulfills its contract that was expressed in English. And the idea of TDD is you'll write a little test, implement just enough code. You do that first, implement just enough code to get it to pass, which could be like if the first test just asserted 0, square root of 0, 0, then I would just return 0 hard-coded. That was the test-driven development idea. And I write the next test would have one assertion, square root of 1 is 1. I might just return whatever you pass in, right? So far I've passed 2 tests, and the idea was I want to build up an interesting body of tests. So my third test might be the square root of 4 is 2. Well, now I actually have to implement my algorithm. So that's kind of what you would do. And now I'd have 3 good tests. But what I think was important and useful about design by contract that's lost with test-driven development is I don't have that specification. I just have like, here's a few examples that I want to make sure work. I mean, I still have the contract. It's written in English, but I don't have more of a formal way of writing the contract that you had in design by contract. So where you can get that back, because like this guy doesn't say, well, for 1, 0, and 4, this should hold true, right? That's what we tested. It says for any x that's passed in, right? So you can get that back if you use a property-based test a la quick check or Scala check, and because that has a for all in it. So it says for all x's of type double, so long as, and now we have to repeat ourselves, which is not a good thing. I'm repeating the precondition in my test and in my require clause, but if that precondition holds, then there's the postcondition. That's the same postcondition we had before. So using a property-based test gets back that expressiveness of the design by contract. And so one of the talks I gave a few years ago was called The Essence of Testing, and what I claimed was that this little statement of predicate logic is the essence of a test. A little upside down A is for all, and then X here will be of type double. So for all X's, P and Q are called predicates in predicate logic, which are like, you can think of them as functions that return Boolean. So if the P predicate holds on X, in our case, you could write P to be the precondition right there in Scala. That implies, the right arrow implies, that Q would hold on the input and the result. So f of x, f is our square root function. F of x is the result of passing whatever x was to that. And then my Q will operate on both of those. So my Q takes both the x that was passed into square root and the result it returned, and it does its postcondition, right? So that's what I think a test is that. It's like you can express a test as a statement of logic. And it also is like a specification of the behavior of the function, right? Okay, so the other idea that I gave a couple years ago, a talk called Hope, Faith, and Proof. And in there, I talked about when to use assertions in production code. And one of the things I think is useful is to use require clauses if it's a partial function. Square root really isn't defined on numbers less than 0, doubles less than 0, so you should say that at the top and blow up if right away, instead of like letting that percolate through and the code doesn't know that there was a bug until sometime later after they've already corrupted data in the database or something. You want to fail fast. But every time you use a require, I think it's good to think, can I move that to the type? So if I move it to the type, like this, let's say, this is a double that's positive, 0, and finite, which means it's also not a number. So if I actually have a type, then I don't need that require clause, right? And what I want to point out about that is that means that we have faith that types will implement their contract. So like if you have a function that takes an int, you don't do a require that the int that's passed in is greater than or equal to int.max value and less than equal to greater than equal to int.min value and less than equal to int.max value. Because we just assume it will be. Even though we know sometimes there are bugs and sometimes types don't implement their contract, the way we program is that's the thing we hang our faith on, that's what we believe fulfills its contract. Okay, so those are the two things that I wanted to start out with, is just that you can specify a function and test it with property-based tests with a little statement of predicate logic of that shape, and that we trust types to implement their contracts in practice, right? Okay. So now what I want to do is write a function to add two natural numbers. And a natural number is 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So I can't really enumerate all the natural numbers because it goes up forever. But what I can do is define them inductively. So what this is two little rules that defines natural numbers. And the little line, the horizontal line, is kind of like if on top, then on the bottom, right? So if and the one on top, there's nothing in the if, so it's if true, then 0 is a natural number. So I'm just kind of saying, let there be 0. 0 is something I sort of just invent and say that it's a natural number. And the bottom one says, if P is a natural number, that's the top line, then the successor to P is a natural number. So with just those two rules, on day 0, I can get a 0. The next day, I can get a 1 because P is 0, and the successor to P is also a natural number. Now I have 1, and the next day after that, I can get a 2 because you say, well, P is 1, so successor to P, successor to 1 is a natural number. I get 2, right? So in Scala, you can just write it this way, and I'm going to demo this. So I have a sealed trait nat, and it has a 0, object 0 subtype of nat, and it has a successor that's also a subtype of nat. And those are the only two possibilities. And successor takes a predecessor, that's what the P is. So I can just demo that guy. So I can just say 0, that's a natural number. I can say the successor to 0, 0. if I can type it. So there's 1. And you can figure out what number it is by how many sucks it has in the expression. So that's suck 0, that's 2, because I said suck twice. So that's basically the idea, and I can keep going forever, but you get the idea. Okay, so far so good? So that's a basic natural number data structure. And so now what I want to do is I want to make a plus method on it. So I'm going to add, well, I just did that, so I'm going to add plus. So to the nat trait on top, I just said the signature of my plus method is it takes another natural number and it returns a natural number, right? So that's an abstract method. And then in the 0, I'm going to implement it by just returning the right-hand side. So R, it's just what I call the right-hand side. It's what you pass to plus, essentially. On 0, it just gives back the same thing. I think that's the correct implementation. And then in my successor case, what I do is I say that I'm going to claim that the successor to P plus some R is going to be the successor to P plus R. So it's just one more than the addition of P plus R. And what I did is I reduced the natural number by 1, because P is 1 less than successor of P. And then that would recurse all the way down to eventually you'll hit 0, which doesn't recurse anymore. So that's the idea. So let me just demo that. Grab that guy. And after all this technology, I'm going to add very small numbers. Here's 0, 0. So 1 is going to be the successor to 0, right? And 2 will make the successor to 1. And let's do a 3. Oops, 2. Okay, so I have 1, 2, 3, 0, 1, 2, 3. So 0 plus 0. Anyone? Anyone? 0. So that worked. You guys can go ahead and do these in your head. You don't have to embarrass yourself to get them wrong, right? This is working. I can say 2 plus 2 is 4, because you can count 4 sucks, right? 2 plus 3. So it looks like it's working. Now, at least it works for 0, 1, 2, 3, right? But now what I want to do is express something about the contract. I'll just pick one thing, which is addition is supposed to be associative. So I go back here. Essentially, I want to say this is, I want to advertise to you, the users of my natural number library, that addition on natural numbers is associative, and then I want to make sure it. I'm going to actually make sure that I fulfill that contract in my service to you as the library provider, right? So what that is that if you add A plus B first and then add C, for any 3 natural numbers A, B, and C, that's going to equal adding B plus C first and then adding that to A, right? That's associative. And so one thing I could do is I could make test-driven development, right? I didn't do that, but I could do test second, right? Test second development and actually write a few examples. So I have 1 plus 2 plus 3 equals 1 plus 2 plus 3. We can actually do that, see if it works, because we have these. 1 plus 2 plus 3 equals, is that how I did it? I think I did it wrong. Ooh, I did it wrong. Hang on a second. Let's do it right. Yeah, I did it this way. Doesn't matter. Either way, 1 plus 2 plus 3, and this should be true. Okay, so I did one example-based test, right? I could have one that adds up to 42 because I think that's important. It's the most tested number. And keep going, but I can't, of course, test everything, right? And what I really want to say is that for any A, B, and C, or for all A, B, and C, this equality should hold. That's what I want to say about my function. And there's no, this is the Q, really. It's the post condition. It's not a precondition. There's no precondition. Any natural number will work. So I can do that with a property-based test, like that. I just say for all natural numbers A, B, and C, and then I have my associative equality check. And we can try that because I have that happen. It's kind of like a cooking show. I have that already finished over here. And all we have to do is wait for IntelliJ to compile it, probably. So this would be a good time for music. Okay, that actually, you can't see this teeny tiny little thing. It does pass. But I also inserted in this a little info so you can see what's tried. Essentially, I'm saying for all, but I'm really just doing example-based testing still. So I'm going to run it out here so you can see the two strings. Let's just say test. This is running the same test. You can see that here I tried 31, 34, 62, 13, 76, 63. You can see what those look like in, in my memory inefficient natural number representation. And the reason is, if you look at my generator, when you do property-based testing, you need a generator to generate the type. So I'm generating natural numbers by just taking ints between 0 and 100 and trying those out. So I never test anything above 100, and I now test all combinations of 0 to 100 because it's just, that's ridiculous. It's too many, right? So it's still, there could be some set of numbers, even between 0 and 100, that don't pass this test. And my, there's like a correspondence between the way we do software testing is a lot like science. What science does is scientists think of hypotheses. Like I think this is how something works in the universe. And then they don't just like publish, hopefully. They do experiments. They come up with experiments and they test their hypothesis, right? And so we have the hypothesis that our code works. Like I have the hypothesis that my plus method on natural number is associative. That's my hypothesis. But I actually write a test to do it. But what I call this maybe Einstein because he's often quoted. I see him quoted saying this, but I can't find evidence that he actually said it. And I keep finding evidence that people say, well, he never said that. So maybe he said it. But it's a good quote about science. And what he said is that no amount of experimentation can ever prove him right. But a single experiment can prove him wrong. So relativity has passed a lot of tests, right? They've done all kinds of experiments over the decades, and it's, it works. Doesn't mean that tomorrow there's not going to be some experiment that says, oh, actually in this situation it doesn't work. And that kind of is what he did to Newton, right? For, I don't know how long Newton's laws that people thought they worked because they were looking at larger things, and when you get to smaller things, they don't necessarily hold, or near the speed of light, things like that, right? So the question is, can we do better than Einstein as programmers? And I think we can because our code is like math, and what mathematicians do is they do proofs, right? I mean, that is math, right? 1 plus 2 plus 3 is associative. So I could do a proof by taking by taking one of these sides, and I start with that, and doing some transformations to it that are valid in my belief that they're valid, and then I end up on the right-hand side. That proves that 1 plus 2, if A is 1, B is 2, and C is 3, that addition is associative for those guys. So I'll start with the left-hand side, and then I can take 1 and 2 and say, well, that's the same thing as 3. And then I can say, well, 3 and 3 is 6. Well, 6 is 1 plus 5, right? And 5 is the same thing as 2 plus 3, and therefore, I've proven it. So that's a proof, sort of how you do it. But this is kind of like a unit proof. I could do another unit proof for that other test case. So I'm like it is a proof, but it's like not a proof that all A, B, and C, that holds true, right? So I wanted to illustrate how one might do that. It's not easy, and this is probably like one of the easiest proofs we could come up with. So it's very difficult to do proofs in practice about things. But what I'm going to do is I'm going to try to prove that thing on top for all ABC. My implementation of natural number addition on my data type is associative. That's what I want to prove. So I'm going to use the code. So like if you look at the comment, the lower comment that says 0 plus R equals R, you can think of the left side of that as if someone calls that at the client, in the client code, calling into my library, into the plus method, what I'm kind of going to do is I'm going to execute the right-hand side. I'm just going to return R. So you could just replace that. I mean, if this code was inlined, it would just replace 0 plus R with R, right? So that's an equality I can use, and I actually want to use my implementation because I'm trying to prove my implementation meets its contract. And then this one, at the call site, somebody has a successor, which means there is a predecessor. If you add R to that, then you could replace that with the right-hand side, saying that if you add the previous natural number to R and take the successor of that, that's going to be the result. So I can, given the shape on the left, I could replace it with the shape on the right in my proof, and vice versa, right? Those are equal. So So that's what I have. And the other thing I'm going to let myself do is add and remove parentheses. But I'm just going to say this is what I'm going for, and I'm just going to take these two equalities and try to prove, with those two things, the thing on top. And so I can't do it by enumerating. I mean, we've already done two of them. 1, 2, and 3 past this, and the other one I did was 12, 7, and 23. But there's just too many combinations, right? So I can do my proof inductively in the same kind of way we defined that natural number to begin with. I can say, well, I'm just going to try to prove this 0 case by hand-coded, just kind of like I proved 1, 2, 3. I'll just prove that one. And that will be just sort of no precondition. And then given a p, some natural number p, if it's associative with any b and c, then I want to prove that the successor to p is associative. And so now that I have 0, I can plug in 0 for p, and I've proved that 1 is associative if 1 is a. If I have 1, I can now plug 1 in for p, and now prove that 2 is associative, and it goes on forever. Basically, I've proved that my implementation is associative. Okay, so that's what I'm going to try to do. So if you want to look at it as an algorithm, because we're programmers and we think, like programming, I would say if a is 0, then I need to prove the top one. Else, it's definitely successor to p. That's the only other case. So I have a p, and all I need to prove is if the p case is associative, then its successor is associative. And that will give me my proof. Okay. So this one is pretty much similar to 1, 2, 3. I start with the left-hand side, right? A is 0. And then I just say, well, I have that rewrite rule, essentially, that 0 plus r is r. So let me just get rid of the 0 there, and I have b plus c. I can take the parens away. I can reparenthesize. That's allowed. And then if you think of b plus c now as r on the right-hand side, I can go back leftwards and stick a 0 plus in front, and that's allowed, right? That's just, and I actually proved it. So that's my 0 case. That was pretty simple. It's like just as easy as 1, 2, 3. Actually, that's the same technique, right? Okay, so now the more tricky one is successor. So what I have here is I'm going to assume the top part. Like I have to prove, given the top part is true, prove that the bottom is true, right? So I'm taking this as a given, or the thing on top is like an axiom. That's just believed to be true, and now can I prove the other one, right? So I'll start with the left-hand side again, where A is now successor of P. And the first rewrite is the shape of the thing in the parentheses is, well, if you, is the which one is it? The shape of the guy in parens is the shape of the left-hand side where P is Y and B is R. So I can rewrite it to the right-hand side. Just the leftmost parens I'm rewriting from left to right of that rule. So successor of P plus B is what I changed. So I just changed that one inside part. It gets a little bit hard to follow, but this is kind of illustrative of how these are tricky to do. So now I just removed that one set of parens, and I have this shape, right? And so now what I can do is I can go and re-parenthesize, because if you think of P plus B in this case as Y, then I can say, well, that's the success. I mean, did I say left to right? I go left to right, yeah. So in the previous line, Y is P plus B, and R is C. So I can rewrite it the right-hand way where the whole thing's in parens. It's the successor of P plus C, right? So now the problem is I'm a little bit stuck with my rewrite rules. I can't really use one of them. But what I can do is remember that I'm assuming that P is associative, right? So if you look inside the parens here, and ignore the successor thing for a while, I have P plus B in parens plus C. Well, that was, if I go back to my little guy here, P plus B plus C, I could rewrite it to the right-hand side of the top line because I'm assuming that, right? I mean, that's one way to look at it. The other way to look at it is I'm actually recursing using the same proof. So see how I just rewrote it to the right-hand side? That's my assumption or my axiom. And now I just do one more rewrite and I've got my, my proof. So that's a proof that our implementation fulfills its contract of associativity. And those are really hard to do, but that's kind of the idea. Okay. So, what the point of this talk that I wanted to get to is that I do like design by contract's formal specification of contracts with code. But I didn't like that these are things that can blow up at runtime, right? So if you actually are able in your language to attach little statements of predicate logic to your functions and to your classes, to your bits of code, then that is how you can specify the behavior in a more formal way. I think that's a good thing. And then you can reassure yourself that your code is fulfilling its contract in two different ways. One is you can write a property-based test, which is really like a fancy example-based test, but it's got a lot of nice properties, so to speak. But you can also use a proof. In other words, it's the same input. So this is like a way to specify the behavior, and then it's a starting point for either testing or proving. And proofs are very hard to do a lot of the time. So what I think a lot of dependently typed languages, they kind of try to prove everything, and they turn off partial functions so that you can't use the bottom type to sort of prove things that aren't true. And I don't think that's necessary to get value out of it. What I think that you can do is look at each proof individually, and you just take the types that are involved in your function, the things that are passed to you, the things that you instantiate, use internally, the thing you return, all those types you just assume, you take it as an axiom that they fulfill their contract, even if it's not been proven, even if it's just tested, because that's actually what we do anyway. So the function that takes a natural number and converts it to an int, I would assume that right there that natural number fulfills its contract even if I haven't proven everything. And I would assume that int fulfills its contract even if I haven't proven anything. And if this code is simple enough, maybe I can actually prove that code fulfills its contract so long as, and it would be like the thing above the line is all the types that are involved fulfill their contract. If that's true, then my method actually fulfills its contract. So, and that's because in types are the things that we trust to, it's what we believe. This is real, I feel like I'm in church here, but if it's what we believe is actually true, even though we know sometimes it isn't. So that is my talk. I just, before I take a couple of questions, Artima, we do consulting, so if you're interested in joining us, talk to me. If you have Scala issues you want to someone to help you with, you can contact us. And then I'm also on the Scala Center Advisory Board, and I represent the community. And people in the Scala community are not complainers in general. So I actually find it hard sometimes to gather. It's like pulling teeth. Like, what are your pain points? So please feel free to come up and talk to me and complain to me, or just tell me what your concerns are, and I can take them back to the Scala Center. So that's all I have. So we've got a couple of minutes for questions if anybody has a question.
And I have a mic.
Hi.
Are you suggesting maybe we should go back and read Meyer's Eiffel book and take that to heart?
No. Meyer's Eiffel book is quite large, and it's got a lot of, I think he fleshed out a lot of interesting things. I went back and read it, like all the stuff he wrote about various things, but what I like about design by contract was that it's a formal specification of the contract as opposed to what we use, which is English. This is like, going back to that slide. This is what's a little bit, think, wow, it's way back here. Second slide, I think, that one. I think there's something better we can do. I think it should be off to the outside. But no language kind of lets you attach logic as a statement of contract at this point that I know of. So there's one over there. Okay. I don't know. I think the people who design programming languages or tools that help us ensure code is correct could do this. You could do this from the outside too. Like there's test frameworks that are external, and there could be proof frameworks that are external that let you do proofs. But proofs are really hard. So my point was that by using a statement of logic, you can either use a test or a proof. And then proofs don't have to really, they can assume that everything is correct. And then your proof is simpler, it's more small. So yes, somebody had a question out there.
Yeah, so I think that JML allows you to do like first order logic in Java.
Okay.
Is it possible to use it in Scala to accomplish what
Oh great,
you're
okay,
trying
I'll
to do?
try JML. Is JML let me do proofs? Or
No,
does it just let me?
No, I don't know, but you can write like for all statements and stuff like that. Like,
Okay, I'll take a look at that.
okay.
JML. Is anybody else? Yes. Are you? Yes. That one. Yes. Right. Yeah, that's a great comment. I'll repeat it since you were on the mic. He just said, did I not just essentially move the problem to the call sites? Now, before the problem was in one place, the potential, and now it's in 100 different call sites. And so what I talked about in the Hope, Faith, and Proof talk, that's kind of a long version. The short one is that what I think often is a case at the call site is that you have nearby evidence. So I called a require as an expression of hope. As the designer of this function, I hope no one ever passes a negative number, but I don't know. Whereas at the call site, usually it can be an expression of faith. I have nearby evidence. I did something, I just squared it. And so I have faith that that will always be positive right next to, right before I call it, or something like that. So that's one of the points of that Hope, Faith, and Proof talk was that another kind of assertion that I think is good is when you assert that it's positive there and move it to the type, and now it's in the type, because in types we trust, right? A lot of times, like in the Scala book, there's a algorithm for doing quick sort, where there's one function that takes a sorted list, but it's not in the type. So if we could, assert there because I have evidence that I know it's non-empty, or that it's sorted because I just sorted it, or whatever, then that's better. I think it's better, even though there's more places where it could possibly blow up. At each of those places, if there's evidence nearby that will always succeed, then I think that's another kind of assertion that's good to have in your production code, because right away you move that thing you just proved with an assertion at runtime into the type. Okay, yes, oh, sorry, hi.
Yeah, I was just wondering if you had looked at the Stainless project and if you had any thoughts on that.
Yes, Stainless. I have. I will look again. Yeah, I have looked at Stainless. I think, yeah, I don't want to say anything about it that might be incorrect. Do you know, can you summarize what it is, Stainless? Without the mic? You can give the mic, yeah, just give it a summary.
So it's a project from the Lara lab at EPFL to sort of add a lot of the predicate logic-based formal verification that resembles what you were describing
Okay.
To a subset of Scala.
Great, to a subset, yeah. It uses a subset of Scala and tries to do that. I have looked at that.
I have a question.
Oh, yes, sure.
It's actually interesting that you mentioned the word church, which happens to be the last name of a famous mathematician and
Yes,
the
I've
founder
heard of this guy.
of lambda calculus. What about the fact that no axiomatic system is complete? So basically, there'll be a bunch of true statements that will never be provable.
Okay, this is kind of the church of church.
Exactly.
Right? The Scala conference. So what you said is like, no, it's not complete. I'm not sure how that affects proofs. What I have, I would say that essentially, I may not be able to, let me just go back to the last slide. I may not be able to prove everything. And I think that's okay, because we don't prove anything today. I mean, so if we can do a few more that are actually proven, imagine if the standard library had a lot of proofs. That might be useful. But then they find a faster way to do something where it's hard to prove, and they re-implement it to be fast, and they just keep the same contract, and they just test. I think that's okay too. So that's kind of a fuzzy answer, but I just think it adds value even if we can't prove everything.
Totally agree. Thank you.
Yes.
Apparently, Scala 3 is going to have bases on dependent types. I don't know if that's going to be exposed, but how does that affect the creation of types and so on?
Yeah, so dependent types is a way to do this. I think what a proof framework would look like for Scala is be like a little dependently typed language that knows how to like do these kinds of rewrites. These guys right here, where are they? Yeah, like the things here, which you'd have to have inheritance and that kind of stuff. I'd have to understand that. But the Curry-Howard isomorphism, I think it says two things to me. One is that there's something fundamental about this, type theory, that it was discovered and it came along in three different ways. There's also a category theory kind of branch of it, that independently people came up with the exact same thing. And it also is, like for programmers, it's a great way to do proofs. You don't have to do it on pencil and paper. You can actually code this in Agda or something, or some proof framework or something, and that's how we do it. That you can express that thing in top as a type of a val, and then if you can actually write a code that compiles, you've actually proved that for all statement. And it's for programmers, I think that's the way we would do it. Probably, yeah.
All right, that's the time we had for questions.
Well, thank you very much for
Thank you so much.
Come and talk to me if you have comments about it. Thanks.